like to go forward now to the next talk from George Gekov. He is an senior application engineer in Arm's machine learning team. George helps Arm partners with firmware design, performance evaluation, and neural network optimizations for SoCs dedicated for machine learning. Prior to working in machine learning, George was part of Arm's IoT team and created numerous demonstrations of connecting low-power devices to the cloud. He holds a master's degrees from Cambridge University and the Sorbonne University. So please give him also a warm welcome.
Very good morning. Can you hear me at the back of the room? Yes, okay. My name is George Gekov, and I work as a machine learning applications engineer in Arm. And what this means is that I get a chance to interact with the various Arm partners who are building machine learning system on chips. So, and I wanted to share with you some of the learnings that I've gained throughout the years and speak about what you need to know in order to create tinyML applications in the cloud. I think I can pretty safely say that creating tinyML applications is difficult. First, you obviously need to have the business case, but you need to have the high-quality labeled data. You need the neural network architecture that is going to match your data sets. And you also need to have knowledge about the embedded software. So I'd like to speak a bit about the key principles when you create the embedded machine learning software. And also I'd like to touch on some of the common pitfalls that I notice in the creation of neural networks. But first, a couple of words. I think most people are probably familiar with what is the Cortex-M. This is a general purpose microcontroller. Very, very capable to run machine learning workloads. Modern Cortex-Ms, they even come with vector extensions. For example, M55, M85 is having the MV vector extension. But really, if you want the best performance per watt for machine learning, you have to start with a piece of silicon that was designed from the ground up for this purpose. And that's where the Ethos-U product family comes in. So the Ethos-U is actually a dedicated hardware accelerator that is going to be doing multiplies accumulates in parallel of your machine learning workload. And I'd like to draw your attention there to the number of, to the bottom of the slide, the 800x improvement in performance. This is actual acceleration that we have verified in silicon. This is not coming from our marketing department. This was run on the chip of Aleph Semiconductors, the first company to adopt the Ethos-U55, and it compares a machine learning workload running on a Cortex-M4 compared to running it on an Ethos-U55 in this case. And I'm going to speak about some of the principles that you need to be aware of if you want to be able to generate this sort of uplift on your systems. So what is the main software stack to be running machine learning on a Cortex-M today? The main software stack actually relies on TensorFlow Lite Micro. This is not the only option, but it's one of the sort of, shall we say, the most widespread option. And with TensorFlow Lite Micro, you're having the reference kernels, which means that whenever there is a new operator that appears in TensorFlow Lite Micro, this new operator is actually going to run on the Cortex-M, probably not in as efficient way, but it's going to run. So this creates a very robust story, which is absolutely essential for machine learning because there are new operators that are emerging every single day. And as you know also, even though machine learning operators are not necessarily very complex, there can be a lot of details. For example, even on an operator such as, let's say, conv2d, you can have an awful lot of attributes. You can have different dilation rates, and we're starting to see sometimes exotic dilation rates, such as, for example, 100. You can have a wide range of strides. You can have groups parameters. And all of those attributes are going to run on the Cortex-M. So this means that the Cortex-M is also very flexible for running machine learning workloads. And with CMC-CNN, you can also leverage the DSP extensions or the vector extensions on the Cortex-M. If you want to get silicon acceleration on your workload, we also provide the Ethos-U microNPU, as I was speaking about in the previous slides. And in order to use that, you need to optimize your model with a compiler, the Vela compiler. I think some people in the room are already familiar with that. And what the Vela compiler is doing is that it takes the machine learning model and essentially it maps it to the block-based Mach engines of the microNPU. And of course, we are getting an awful lot of performance, but you have to be aware that we do this by restricting some of the operators that we can use. The Ethos-U55 and U65 is having this notion of supported operators. Some operators are just not suitable actually for silicon acceleration, so we had to make a decision for what are the operators that we support. But I also have to say that because we're having the system with the Vela compiler, we are able to add support for new operators in software where relevant. And how do you run an inference M today? Well, we're going to leverage TensorFlow Lite Micro, and in this couple of slides, I'll speak about the inference alone. Obviously, machine learning is a lot more than just an inference. I'll speak about pre-processing and post-processing and later on, but for now, let's focus on the inference because pre-processing and post-processing is usually specific to a given neural network. So to run an inference on the Cortex-M with TF Lite Micro, you just have to map the model. You'd have to pull in the relevant kernel. So let's say your model is having conv2D. You're going to create what is called micromutable resolver with the conv2D kernel. You'd have to build an interpreter. You'd have to allocate memory, obviously. And you just need to run an inference with an invoke. And those are steps that are really generic. This is going to work from Cortex-M0 all the way to Cortex-M85. Now, I want to ask you, what is going to change if instead of having a Cortex-M, you also have a system on chip which has Cortex-M and Ethos-U in your embedded software? The only change that you'd have to make is that you'd have to pull in the Ethos-U kernel that is already part of TF Lite Micro. All of the other stages, all of the other code in your embedded firmware is going to remain unchanged. So this creates a very, very convenient way to pass from running a machine learning on Cortex-M to running machine learning on Cortex-M and Ethos-U. Now, this is looking into the embedded software. But for machine learning, obviously, a very important part is the neural network that you're running. So the next couple of slides, the next two slides actually are about those of you that really want to get maximum acceleration from your from your system on chip, and you want to be able to achieve this 800x improvement in performance, what I was speaking in the first slide. So what are the pitfalls to avoid in the neural network design phase? As I was explaining, in the Ethos-U, we have this notion of hardware-supported operators. And what I'd like to say is that it is really beneficial when you design the neural network to be aware what are those operators that can be accelerated in hardware. So I'm going to define a simple neural network here. I have a convolution 2D, and I'm having a resize bilinear. Please take a look into the resize bilinear operator. The resize bilinear, I'm passing from 32 by 32 height and width straight to 128 by 128. So I'm doing upscaling by 4x. This is very common in, for example, DeepLab-V3 models for semantic segmentation. This is sort of a structure that you're going to find towards the end of DeepLab-V3. And you have to know that resize bilinear with an upscaling factor of 4x with half pixel centers attribute set to true is an operator that unfortunately is not supported on the Ethos-U. And that's absolutely fine. We can see that this is not supported when we compile this model. We're having the convolution 2D, which is going to map to the Ethos-U. You can see the Ethos-U there in the graph. And the resize bilinear is going to be offloaded to the CPU. That's absolutely fine, and this is going to run on the system in 74 million cycles. So the Ethos-U operator is running on the NPU, the resize bilinear is running on the Cortex-M, and it all takes 74 million cycles. Now, I'm going to define the exact same network, but this time, instead of doing a single resize bilinear with a factor of 4, I'm going to do 2 times resize bilinear, each time upscaling by a factor of 2. So the input feature map and the output feature map is the same. I'm still passing from 32 by 32 to 128 by 128. I just do it in 2 goes. Compile the model with Vela, as on the slide on the left. I obtain the graph here, which contains a single Ethos-U operator. And when I run this on the hardware, we see that this runs in 1.2 million cycles. So I fully recognize that creating neural networks is quite complex, but I just wanted to say that it really pays dividends to be aware of the operators that are supported in hardware when you're creating a neural network, for those of you that want to get absolute best performance of your machine learning workloads. I want to say a couple of words also about weight compression. If you were at the last tinyML summit, you probably heard the presentation of Ian Bratt, and he was speaking about how an inference is incredibly data intense. Data intense in the sense that there is a lot of reads and writes to and from the memory. And what this means is that you basically have to come up with an efficient way to interact with the memory if you are to ensure that you are having very, very good performance. And this problem is so important that we even have silicon area dedicated to interact efficiently with the memory. So the way that what we're having is that the Vela compiler is able to compress the sequence of weights. Or actually, Vela compiler is essentially doing the weight compression of your neural network. So for example, it's going to compress sequence of 0 weights. And it's also going to compress clusters of the same weights. And then this data is going to, so the compressed weight stream is going to be fetched by the hardware and decompressed. And you're going to save a lot on memory accesses. So what do I have here? I have a neural network with 3 fully connected layers. Fully connected is very well known to be memory-bound operation. It's memory-bound because you're multiplying everything by everything, so you have a lot of data that needs to be read from memory. And when I run just the baseline model, I'm obtaining 91,000 cycles. Next, I'm going to prune the model. When I say prune, I mean that I'm going to set 80% of the weights of the model are going to be set to 0 by the end of the pruning. TensorFlow provides already the pruning APIs, and the way this works is that you're having your trained model, and then you set randomly 50%, in my case, 50% of the weights you're set randomly to 0, and there is an additional retraining that is done. The Vela compiler is obviously going to encode the sequences of 0 weights efficiently, and then the Ethos-U hardware is going to run this workload, and you're going to run it in 34,000 cycles. So nearly 3x reduction in the amount of, essentially in the amount of processing time. This model, for this model, I'm using the MNIST dataset, and that's where the accuracy figure is coming from. And lastly, in addition to the pruning, I'm also going to apply clustering. So I'm going to be using 32 clusters of weights. And as you can see, this is adding an even further uplift into the performance that you're getting. I'm speaking here about number of cycles that the NPU is executing, but this reduction in number of NPU cycles is actually coming from the lower number of memory accesses. So there is going to be actually a significant power saving as well. And also the size of the TF-Lite file that you have to store on device is going to be significantly reduced. I have a detailed blog on exactly that point at the link from the bottom of the slide. So I've been speaking about inference so far. And machine learning is so much more than just an inference. So how can you run an end-to-end tinyML application on Cortex-M or on the Ethos-U today? Well, we provide a number of example applications. So you can see the project at the first bullet point, the ML Embedded Evaluation Kit. This is an open source project under Apache 2 license. And essentially, it provides ready-to-use machine learning applications, end-to-end machine learning applications. So we're extracting, for example, the MFCC features. We're doing the inference. We're doing the post-processing. And we have applications about keyword spotting, automated speech recognition, noise suppression, image classification, object detection, person detection, anomaly detection. So all those applications are there so that you don't need to reinvent the hot water when you're starting your development. What can you do with that? Well, you can run those applications, obviously, on Cortex-M, on Ethos-U. You can run them locally on your desktop, or you can even run them in the cloud with Arm virtual hardware. So you don't really need even a development board for that. You can evaluate the performance of a custom neural network. Say that you're having your in-house workload, and you'd like to know what is going to be the performance of your workload when it runs on with silicon acceleration. You can do that. Again, in the cloud or locally. And you can adapt, perhaps the most important point is that you can develop your software and you can adapt your software for the once silicon becomes available, so that you essentially are shortening the time to market of your application. So tinyML, it is difficult, but there is a lot of resources out there that have been designed to help you to get started. And for those of you that want the best performance, it really is helpful to ensure that you are aware for what are the hardware-supported operators of your hardware. Thank you very much.